So, in first place, I would like to apologize a little bit because I had some technical difficulties and I needed to reboot my laptop. But anyhow, we are good to go now. So, in the first place, I would like to really welcome you to this presentation. And for the people who don't know me, my name is Plamen Krastev from the Research Computing Group here at Harvard University. My background is in theoretical and computational nuclear physics and astrophysics. And before coming to Harvard, I was at Lawrence Livermore National Lab for about 3 years as a postdoctoral researcher, developing large-scale shell model computer codes in the context of nuclear theory. And pretty much this is what got me really into the world of high-performance computing. And after that, I really got hooked into that. So here at Harvard, I do a lot of scientific software support, everything from installing and porting of scientific applications to debugging and optimization. I also do a lot of documentation and prepare code examples and deliver a lot of training sessions like this one. So today I'm going to be talking about parallel job workflows on the cluster, where the special emphasis will be on OpenMP and MPI workflows. If you don't really know what is this, don't get disturbed. I guess this will clear out as we move along with this presentation. Since we don't have that many people, I just would like to make this presentation more informal. So if you have any questions during the presentation itself, you can, either put this in chat or also feel free to interrupt me at any time. All right, so let's just dive into the presentation. So our objectives with today's talk are twofold. The first part of our objectives is really to advise you on the best practices for running parallel workflows on the cluster. And then the next objective, although I'm not going to go into very big details about, really teaching you how to do OpenMP and MPI programming, to provide you really with the basic knowledge which is required for implementing and running parallel workflows which involve OpenMP and MPI on the cluster. So this is a very brief overview of the topics that we are going to cover here. First, I'm going to give you some tips about the best practices in general about computing. Of course, the emphasis will be again on parallel computation. And after that, I will give you a very brief introduction to parallel computing, just giving you the very basics and what is really parallel computing and high performance computing all about. And then I will discuss different modes of doing parallelization, in particular, embarrassingly parallel jobs and workflows, or if you wish, pleasantly parallel. And then I'm going to be talking also about OpenMP and MPI, and at the end, give you a glimpse about, doing hybrid parallelization and also running hybrid parallelization on the cluster. These are applications which include both MPI and OpenMP, so that they can make use of the total power of the cluster. And this is definitely a heterogeneous approach. So before we move along, I would like to start with some best practices. And again, these are not only pertaining to parallel computing, but in general. So the very first thing that you need to do is to do a small, scale test prior you start your large production runs. And this is a good practice because it actually ensures that your code operates as required, and you just want to make sure that everything runs before you launch your production runs. Another thing is to ensure that your jobs will run at least for 10 minutes. And this is because 10 minutes is the least amount of time that you can request in Slurm. Another thing is to make sure that your jobs are well constrained, which means that you have to request appropriate computational resources for your jobs. And this includes things like memory, number of cores, CPUs, number of nodes, and things like that, which I'm going to discuss in more details as we move along. Another thing is if your jobs and workflow in general requires a lot of I/O, if you write and read a lot of data, you have to make sure that your jobs are executed at a file system which can handle this high I/O load. And we have parallel file systems which are designed also for parallel I/O, and I'm going to discuss this in more details as we move along. Another thing is you have to be aware of potential bottlenecks in your workflow. In other words, you have to understand very well where the hotspots in your workflow, and then work to parallelize this in particular because most of the computation go in there. Another thing is to be aware of your fair share, because the more computations you run, this impacts your fair share. If you want to learn more, you can go to this link over here, which will give you even better tips about it. Another thing is to ensure that the code operates as expected. I already covered this, but just a reminder. And this also goes with understanding the scalability of your code. The notion of scaling is very important in the context of parallel computing, because basically it shows the scaling shows how faster your code will run as you throw more computational resources. For example, when you throw more CPUs, you expect your code to run faster. So it is a good idea to understand the scaling and where you hit actually the saturation plateau. In other words, when you put more resources, where is actually the point where basically the code doesn't speed up anymore. Another important point, which I would like to emphasize really, is to have your primary code into a Git repo, and this goes together with keep critical data, in backups. And I can't really emphasize this more. It is absolutely critical and vital to have backups and copies, in particular of your production research codes, and also any critical data, which, for example, is required to reproduce published research. Another thing is, once your code is running, you may implement checkpoints. Checkpoints would allow you to recover from a potential crash, let's say. If, for example, for unforeseen reason, the code crashes, whether due to software issues or due to hardware failure on the cluster, you will be able to restart from where you left. So potentially this can save you a lot of time. And once everything runs, you can work actually to optimize your code so get the best performance on the cluster. So after this general pointers for good practices, I'm going to give you a very brief introduction to parallel computing. So what is really high performance computing and parallel computing, or HPC? So for the purpose of this presentation, I'm going to use the words parallel computing and high performance computing, or HPC, interchangeably. Although strictly speaking, is this not correct? High performance computing basically really pertains to using the world's fastest and largest supercomputers to solve large and complex problems. And here, just to give you a glimpse, we included several computers from today's top 500 list, which basically is a list which compiles the fastest and largest platforms on the planet. So I think the first place is still retained by Frontier at the Oak Ridge National Lab. Next, we have Sierra at Lawrence Livermore National Lab. And we also have Canon in the top 500 also, although it's not really on the third place, but it's really a great platform of to which you have access so that you can do, a lot of great research work. What is really serial computation? So traditionally, the software has been written really, for serial CPUs, which means that in this paradigm, when we have a problem, the problem is broken into discrete sets of instructions, and each set of the set of instructions are executed one after another, and only a single instruction can be executed at every single time. So that's why everything is in a serial mode. So in contrast, in the simplest term, when we go to parallel computation, basically, again, the whole problem is split into, discrete parts. And then each part is further broken again into a set of instructions. And again, each set of instructions is executed one after another, but for each part on a separate CPU. So this would allow you, concurrently to run much faster because you're using many more CPUs. And this is one of the major reasons actually for using high performance computing. The major reason for using high performance computing, as I said, is that potentially it can really speed up a lot your computations. And let's say if you have a problem which in serial can take a month to run, if you have access to a cluster like Canon, and if your code is well parallelized, you may be able to complete your workflow in a day, for instance, which would really save you tremendous time. Another very important reason for using HPC or parallel computing is the ability to solve much larger and complex problems. For instance, some problems can be so large that you won't be able to fit, the whole data set or the whole problem into the memory of a single computer. And for example, when you have access to many, computers which are interconnected to make a cluster like Canon, you can distribute the data across many computers. So effectively, you have one large computer. Another thing which is important in the context of HPC is that HPC also provides concurrency, which means that if you have access to multiple resources, you can do many things at the same time. In other words, you can solve, for instance, even many different problems on these computational resources and get much faster results. And also you can use non-local resources. For example, our cluster Canon resides in Holyoke, which is Western Massachusetts. You don't have to need to take a trip to there, it's just only enough to open your laptop and open your terminal so that you can connect to the cluster. So you immediately have access to a much larger resource. So this is some list of applications of HPC, although it's not really a complete list. It really includes it lists most of the traditional ways of using HPC. So HPC is used in physical sciences like atmosphere, Earth environment, space weather, physics, astrophysics, pretty much in all the realms of these disciplines, chemistry, geology, just to name a few. And like I said, this is by no means an extensive use. Recently, HPC has a lot of usage also in AI and in machine learning and deep learning for training, neural networks to do amazing things. So this is also one very important application of HPC. In addition to that, it also has applications in social sciences, economics, business, and pretty much everything that you can think of where data is involved. The next thing that I'm going to cover now, I'm going to cover several different modes of doing parallelization. So we're going to start with embarrassingly parallel, and just to put this in the context, if you have a sequential code or serial code, and you have many data sets that you need to process or different parameter sets, if you have a sequential code, you just have to start with some parameter set with some input, then you feed this into your serial code, and then you you crank the numbers and you get some output. Then in a sequential paradigm, you just have to go back, get the next set, and so on and so forth. So embarrassingly parallel would mean if your data sets are well, there's not a lot of dependence between them, you would be able pretty much to run many different instances of your serial code, each working on a different parameter set, but all running at the same time. So you can go massively parallel. So this is what refers to embarrassingly parallel or pleasantly parallel, if you wish. So, for example, this paradigm can be used for things like parameter sweeps. If you have to crank, the same code with different parameter sets, when you do data transfers, you can also do that. Or if you have data analysis pipelines, again, pretty much you're doing exactly the same analysis, but over and over different data sets. So if you end up in this scenario, one thing you can leverage on here on Canon is to use a partition which is named serial_req partition, which pretty much makes use of three spare cycles that we have on the PI queues. So you can use that to leverage and process your jobs much faster. While you're doing this, you have to be aware of some potential bottlenecks. One of this would be the I/O. For instance, if your code really needs to read and write a lot of data, you need to run your workflow basically on a file system which can handle this high volume of I/O. And one such system is the Holy Scratch 01 file system that we have. And very soon we're gonna have a file system which gonna have even better performance for this purpose, which is named VAST. Another thing which that we have to keep in mind if you run on the serial_req partition is to keep in mind that we have the req mechanism involved on that and implemented, which means that if a high priority job comes, your job will be basically terminated and then requeued. And this may be problematic for some of the cases if your code doesn't have a good way to restart. For example, if it doesn't have a checkpointing. But in general, if you have, let's say, jobs which run in the order of maybe up to an hour, this queue should be a good way to process your jobs. Another thing to be aware is the so-called Sloan thrashing, which means that if you have many short runs, or if you do a lot of queries on the Sloan job schedule, this can put strain on Slurm, and this is something that you have to be aware of. And there are some ways to mitigate that. So that's why here I just put a slide where I'm giving you just some general tips for submitting a large number of jobs. At the bottom of this slide, we have a link, which if you follow, you will find all the information which is required for processing a large number of jobs if you end up in this scenario. There are definitely three different ways that we can implement processing of large number of jobs. One of these is using job launcher scripts. In other words, you can use, for example, scripting languages like Python, Perl, R, and so on to construct and submit your jobs. Another way would be to use construct, which we have in Slurm, which is named job arrays, which would allow you to run many instances of the same serial job, each working on a different parameter set or on a different data set, but all the jobs are packed into a single job from the point of view of Slurm, and this is much easier on the job scheduler. For example, if you have jobs which run, many short jobs which run less than 10 minutes, what you can do, you can pack all these jobs in a single job and then implement a for loop within your job submission script, which loops over the parameters or the data sets, and you just run the same code within the same job. So just kind of a genuine warning here. Basically, really resist the urge to use Python or anything else to create many jobs and then submit this as separate jobs, because this can create really a very large strain on the schedule, and this can affect pretty much everybody on the cluster. If you are, for example, unsure how exactly to process the number of jobs that you have, the best way is really to send us a ticket, and then we can sit down and help you. We also have office hours to which we can come with your problem. So let's just go briefly over these individual steps. For example, different ways of doing a large number of jobs. For example, the job launcher scripts, like I mentioned, you can use, for example, languages like Python, Bash, or Perl, for instance, to construct and submit your jobs. Here you have some significant advantages. They allow you for full flexibility and control of your workflow, but the major disadvantage would be the complexity of your workflow. Because if you have some very complex workflow, basically this can become very complex at some point. We have some examples that you may take a look if you, for instance, want to implement this. Another way for submitting many jobs in the cluster would be to use construct in Slurm, which is named job arrays, and you're using basically job arrays to process the data. The major advantage is that this is extremely easy to use, and it is very quickly to implement. And like I mentioned, it is very easy on the schedule because it allows you to pack all the individual instances of your job array into a single job, which is from the point of view of a single job, which simply has many different indices. A major disadvantage to this approach is that your problem or workflow should really fit into the job array style. And what this means will become really clear on the next slide. But if you wish, you can take a look at this example over here, which would show you how to implement job arrays. And I think I want to mention these slides will be available after the presentation. So you should be able to use this as a reference. That's why we're putting quite a lot of links over here, which you can, in your leisure, you can explore. So let's just say a few more things about the job arrays, and in particular about the indexes, because everything in job arrays actually goes around the indexes and how they're implemented. So to implement a job array in your workflow, when you are writing your job submission script, in the as batch option, you include the -- array option, and then followed by the indices. And this table here simply summarizes the different styling of the indexes that can be used. They can be consecutive numbers, for example, integers like here from 1 to 10, or they can be, even or odd numbers if you want. You can have also, kind of a hard-coded implementation and naming convention for your job array indices, or anything else. So once if you decide to do that, then Slurm provides you with some job script variables. For example, the percent a block capital basically unfolds into a job ID, and then percent a is the corresponding job index within the job array, and this is a simple example here how to implement and use that. Let's say to point Slurm to where the standard output should go, and how actually these files are labeled in particular for each job instance of the array. Similarly, Slurm also provides the slurm underscore array underscore task underscore ID variable, which basically unfolds to pick up what is here under %a small. And this is a very quick example on how this is implemented. For example, this would direct the output of this script to go to specific output which is labeled by the job index of the job array. So to implement this into a Slurm job submission script, you can follow, for instance, this example, which really illustrates how this is done. If you're familiar already with job submission scripts, pretty much you see how it looks like. The only thing which pertains to the job array is highlighted here in red. I think I also had to highlight this line over here, which is the actual array option. But basically, this example here, what it does, it uses a job array of 3 job indices where each label is labeled by this integers over here, 100, 200, and 300. So this example is a very simple example which simply sums the integers from 1 to n, where n is here simply the label of the corresponding job array index. So if you go to this example over here, you may see exactly what it is doing, and in your leisure you can try it. So for instance, if you want to access
on the previous slide.
Yep, I'm sorry. Yes.
If you're not running a script, but you're using this, I guess can you interact with, you know what? I think I just figured out the answer to my question. Never mind. Sorry about that.
No problem. No problem. That's fine. I mean, that's actually the best thing. The best thing is to figure this out. Okay. If you guys have any questions, again, just stop me. Feel free to interrupt me at any time. And also at the end of the presentation, we're going to have some time dedicated to specific questions. So basically, this slide over here is an example of how you can access the environment variable slurm underscore array underscore task underscore ID from Python, for instance. So basically, in this way, you just fit this variable into this serial sum, code, which is just a function in Python, and it will spit out the serial sum from 1 to n, whatever it is, in this case 100 or 200 or 300, depending on the specific case that we have. But basically the whole idea is just to make illustration how the Slurm array index can be used within your codes or your scripts. This is just example for Python, but you can do this pretty much in every other language. You can do this in R, you can do this in Perl, you can do this even in C and Fortran. So this is just an example how to access that, and you maybe immediately also see the major disadvantage of this approach, because it actually shows you that your whole workflow should basically be just massaged, so to speak, to fit the job array format. So like I mentioned, if you have many short jobs which are shorter than 10 minutes, for example, you may have some tasks which run even just a few seconds. The best way is to pack this into a single job and then have within the job submission script a for loop which loops over the specific parameters, or it may even loop over some data sets, which are, for instance, name of files that need to be processed or whatever, and then just execute this within a single job in Slurm, like shown over here. So basically, this is implemented through a very simple bash for loop within the job submission script itself. And if you wish, you can go to this link over here and explore the whole example. Over here, it includes the Python code and also the job submission script, which is required to run the example. And you can experiment, and if needed, you can adapt this to your specific workflows. So having said that, now we're moving to the rest of the presentation. And for the rest of the time, I'm going to discuss OpenMP, MPI, and also hybrid jobs and workflows on the cluster. Like I said, if you don't really know what OpenMP, MPI, and in general hybrid usage of MPI plus OpenMP means, I hope this will make this a little clearer. So what is really OpenMP? So OpenMP stands for Open Multiprocessing, and just in loose terms, this really provides application programming interface, which allows you to do programming in multi-threaded and shared memory parallel applications. So this API includes three main parts. One of these is compiler directives that you can include in your code. Also, it has runtime library routines and environment variables. So basically, OpenMP is a specification which allow you to implement threaded parallelization in your C, C++, and Fortran applications. And I think recently there was also implementation in Python, like PyOMP. And I think there's also interface to Java, just to name a few of the available interfaces. So what is really the OpenMP parallel programming model? So this is a shared memory model, which means that all CPUs or all parallel tasks would have access to the same memory pool. In other words, you don't need to do any passing of data between the CPUs because all the data is already available. For one thing, this is a great thing. For another, it's not a very great thing because it requires you, for example, to do specific blocking sometime if you don't want a specific CPU to have access to specific data, but OpenMP actually provides tools for doing this. So as you can imagine, just by its very nature, this is a parallel model which basically runs on a single compute node or a single computer, because it is assumed that all CPUs physically reside on the same physical machine. Another important thing is to mention that the best performance is really to use one physical thread per core, which means that in this way you can get really the best performance. You can do also the hyper-threading in some cases, but if you really aim to performance, it is really best to just map threads per core, which is available on the physical machine. This method also allows for explicit parallelism, which means that the programmer is really responsible for how the parallelism is going to happen. In other words, nothing happens automatically. You should implement the parallelism into your code in the way you want in order to have the benefit of parallel speed up. Also, another important thing about the OpenMP is it doesn't say anything about about the I/O. The I/O in the realm of OpenMP is still strictly serial. So this is important to keep in mind. There are methods to do parallel I/O, but this is done in MPI and I'm gonna discuss this briefly when we get to this point. So just to put OpenMP in the context of other threading language interfaces, application programming interfaces, OpenMP falls together with, if you're familiar with pthreads, OpenMP, of course, OpenCL and CUDA. These are threading languages which allow to program GPUs, also OpenACC, which also allow for programming GPUs. Python also allowed for doing shared memory computations together with R, Perl, MPI, MATLAB. MATLAB provides PCT, which is the programming computing toolbox, which allows for doing shared parallel computations on a single machine, and also, of course, other languages. So how you compile OpenMP programs? So in particular here, we show how to do that for C, C++, and Fortran applications on the cluster. So we support two families of compilers. These are Intel and also the GNU compilers. Intel is commercial, but its compilers are freely available through the one API because recently Intel actually opened the source for these compilers. And GNU provides the GCC and GFortran compilers, which are absolutely open source. So Intel provides ICX to compile C code, ICPX to compile C++, and IFX to compile Fortran code. And the flag that you need to include to make the compiler aware that you are compiling OpenMP application is the -q OpenMP flag. GNU, on the other hand, uses the -f OpenMP flag. And here I have some very quick examples how to compile OpenMP applications with Intel and GNU. The very first thing that we have to do is to load a module, software module, which provides access to the corresponding compiler. The latest version of Intel is available with Intel 24, which is available as a software module on the cluster. And for instance, if you have a C application, you have to use a command line similar to this one over here to compile your application. And here I just highlighted the Q OpenMP flag, which is required to be included when you compile your application. Similarly to GNU, you have to first load the corresponding compiler. And the latest compiler that we have on the cluster is GCC 13, which is available with this software module. And then, assuming that you have a C code, you compile it with this compile line over here. You may go to this link over here, which includes some examples and also a more detailed information about how to compile OpenMP programs on the cluster. So how are we running OpenMP programs on the cluster? So presumably, if you want to run your application, if you want to test first your application, you may request interactive session. And to request the interactive session, you're using the salloc command. For example, you can utilize the test partition. So important point is to request the specific number of cores or threads that you're intending to use for your OpenMP application. And then you have to request the specific memory. And here, like I mentioned, the memory is shared between all the threads or all the cores. So that's why the memory is requested in Slurm by this specific command. So, and then you specify some time, of course, which is the wall time. The next thing that you have to do is to load a specific module. In this case, we are loading GCC 13. Once you have that, you can compile your code just in a way I described in the previous slide. Here, assuming that we're using GCC, the compile and the command line compile command just follows this syntax over here. And again, at the end, you just have to include this flag over here, which specifies that this application is OpenMP application. So once the code is compiled, basically you are ready to run it. If you want to run the code over 4 OpenMP threads, an important point is that you need to export the OMP underscore num underscore threads environment variable, which specifies the intended number of OpenMP threads for your application. And once you do that and run your code, it runs over 4 threads in this case. The complete example is also available of what I'm showing here. So let's say now, after you test it, you want to submit a batch job submission script to the cluster with the same code. The thing that you need to do is to prepare a batch job submission script, which for those of you who already run jobs in the cluster, this syntax should be familiar. The only thing which is important is to include these directives here, which are specific to the OpenMP application, which basically specify the number of threads and also the number of nodes. Like I said, OpenMP is a shared parallel model, which actually needs all the threads to be on a single node. That's why you have to include the dash block capital N1 directive here in your job submission script, just to make sure that all the threads reside on a single node. Then you have to export this OpenMP variable so that you set the number of threads over which your application runs. As you can see here, this is really set to get the slurm underscore CPUs underscore per underscore task variable, which simply unfolds from what you specify here with the -c specification in your job submission script, which is really the number of threads. So this reassures that you don't do mistakes, because if you hard code everything, it's going to be more difficult to change all the numbers every time when you want to run with a different number of threads, for instance. And once you have that, if you name this script, for example, as batch, if you name your script run.sbatch, it is submitted as usual with the sbatch command to the cluster. So I'm going to give you a very quick example, which is going to illustrate the important concept of scaling in parallel computing. So this is a very simple example which illustrates some of the major ideas of scaling in parallel applications. So this is a Monte Carlo approximation of pi. And for those of you who are not really familiar, the algorithm really goes as the following. You start with some, square, and then you inscribe a circle inside that. So then you have to simply do the Monte Carlo sampling and count how many samples are in the square and how many are only within the circle. And then pi is simply, you just divide the number of samples which are inscribed in the circle with those which are inscribed in the square and multiplied by 4, you get pi. So obviously, when you have more samples, you're going to get better approximation. So Monte Carlo methods, because because you don't have data dependence between the samples themselves, they're very well suited for parallelization. So usually this gives you a very good scaling. If you want to run this example is located in our GitHub repository. So here in this slide, I'm simply including some very simple instructions on how to do that. Basically, you just can make a directory in which you want to download or clone this repo. Then just clone the repository from GitHub and load one of the modules, in this case, Intel. Over there, we're including also a make file, which will automatically compile your code when you type make, and just submit the code to the cluster. So basically, the idea of scaling is when you run, for example, over 1, 2, 4, and 8 processors, in particular for this example, to see, for instance, how faster it's going to run your code. That's actually the whole thing. So putting this just into strict terms, basically the scaling determines how much faster the code will run when you put more resources in it. So the formula for the speed up basically is really given over here, where T1 is the time which takes to complete the job or to run the code over one thread. And then Tn over here is the time to complete the same job running over 9, for example, n threads, depending on whatever number you choose over here. So this would give you the speed up, for each number of threads that you're using for your application. Related to this is also the notion of efficiency. The efficiency tells you how efficiently you parallelize your application. And the strict formula for this is this one over here. Basically, it is really the speed up over the number, the speed up for the specific number of cores or parallel processes over the number of processes. Okay, so this is just a quick recap of this exercise with this Monte Carlo code when it's run over 1, 2, 4, and 8 threads. And this is the wall time, or the time it takes for each case. So as you can see, the speed up is strictly linear. So basically, which also to get very good scaling, and the efficiency is really 100% in this case. So this is a classic figure which illustrates the speed up, where you plot the speed up versus the number of threads or the number of parallel processes in general. So in the ideal case, everything should be linear, and as you can see here, we are doing very well in this case. In most of the cases, however, when you get to a specific number of threads, your actual speed up is going to be beneath the ideal speed up, which will show that basically at some thread number, your code starts to saturate, and at some point you're going to have maybe a plateau, which means that throwing more resources, it's not going to need to better performance. You can improve that, of course, but sometimes you may simply hit a limit. So the next thing that I'm going to be talking about are MPI jobs and workflows. So what is really MPI? MPI stands for Message Passing Interface. So MPI is not really a library by itself, but it is really a specification which tells how exactly the parallelization in the distributed memory programming model should be done. So the most recent implementation of MPI is version 3. So the actual MPI library implementation differ, but they all implement pretty much the same standard. Usually different vendors may come with their own implementation of MPI, which is specifically tailored to their architecture. For instance, Intel provides Intel MPI, which is implementation of the MPI specification. So what is the MPI programming model? So in contrast with OpenMP, MPI is a distributed parallel model, which means that basically each CPU, like illustrated over here, has its local memory. In other words, let's say if CPU A needs data from CPU B, you need to have some way to pass this data, and this is where the message passing, comes into play. So basically, you're orchestrating the work of all these CPUs in a way so that they work through towards solving a common problem. So here I just want to mention the total MPI was originally implemented for distributed machines. Nowadays it can run on machines with any kind of underlying architecture, for example, shared memory and distributed memory machines, although the parallel model itself of programming becomes strictly distributed. This means that even if you have all your MPI processors in a single machine, and you still need to do passing of data between the processors. They don't share the same memory space. So this is just in brief about that. One thing I want to mention that MPI provides explicit parallelism, which means that the programmer itself is really responsible for doing the parallelization. So here are some reasons for using MPI. MPI really provides standardization because it is really the only message passing specification, which is nowadays considered a standard. It provides a lot of portability because MPI code, which is developed for one platform, can successfully run on another platform, which has the MPI library. It also provides performance opportunities because, like I mentioned, vendors can implement their own version of MPI, which is tailored down to specific hardware. MPI also provides a lot of functionality because there are a lot of routines and subroutines which can explore the full power of MPI. And also MPI is available on pretty much all parallel platforms. So MPI is can be used in many languages like C, C++, Fortran, Java, Python. Python in particular provides several different MPI libraries like MPI for Python and some others. R also provides way for doing MPI through R MPI. There's also Perl implementation of MPI, and also MATLAB provides the MATLAB parallel server, a formerly distributed computing server. DCS, it is entirely built on OpenMPI, on MPI. And also there are obviously other languages. So how you compile MPI programs? Basically, we provide the OpenMPI implementation of MPI, and also provide the MPI CH implementation of MPI, which is another implementation of the MPI standard. And like I mentioned, Intel provides its own implementation of MPI, which is named the Intel MPI. So the compilers which are available, or these are just wrappers around the compilers, they can compile C, C++, and Fortran applications. And for example, for OpenMPI and MPI-CH, the available compiler commands are the ones listed over here. We have MPI-CC for C applications, MPI-CXX for C++ applications, and the rest of these are for Fortran applications, which are compiled with MPI. For instance, if you have application which MPI application which you want to compile with Intel and OpenMPI or MPI-CH, the very first thing that we have to do is to load Intel compiler, then OpenMPI library, which is compiled with the specific Intel compiler. And once this is done, you can compile your MPI application like shown over here. I'm not going to go through all the others because, as you can see, this is self-explanatory. For example, for the GNU and OpenMPI, instead of Intel, you need first to start with a GCC compiler, and then again load the OpenMPI module, which is compiled with that specific version of the GNU compiler. So how we run MPI programs? Once you have compiled your application, basically, the very first thing that you have to do is if you want to compile your MPI application, the very first thing to do is to request an interactive session, because in this way you can also test your code in a small scale. For instance, if you want to request an interactive session with 4 processors, you just use this salloc command, and the test partition is really the place where we can test your code. So you just request interactive session, then you load the required compilers and modules. First you load the GCC compiler and then open MPI. And then if you have C code, you just can use this command over here to compile it. And in order to run the code through MPI, you use the MPI run command followed by -np, followed by the number of MPI processors that you want to use. In this case, it is simply 4, and then the actual executable that you compiled and linked against the specific compiler in MPI library. And this is simply the output that we get. And this is a example job submission script that you can use if you want to submit your application as a job, as a bad job. So in order to do that, the very first thing is, again, to compile your application. You load the specific compilers and MPI libraries, in this case, GCC version 13 and OpenMPI version 5. And you prepare bad job submission scripts. Again, it is nothing unfamiliar. The only thing is to make sure that you specify correctly the things which are highlighted in red over here. Because MPI is a distributed parallel model, basically in this case, each of the parallel processors has its own local memory. So that's why the memory is specified by CPU and not by node, like in the case of OpenMP. And also you specify the number of MPI tasks, which is done with SBatch -n option. In this case, we request 8 MPI processors. And then the important point is to load the required modulus, which were used to compile your code. And then the actual command for running the code is srun -n, and then the number of MPI tasks that you requested, which is given by this environment variable slurm _n tasks, which simply unfolds from what we specify here with the -n command. Then once we have everything ready, you simply submit your job to the cluster. If you use Intel MPI, the only difference would be to use -MPI PMI2 instead of PMI-X, like in the case of OpenMP. And this is because Intel MPI is based on MPI-CH. It is just a derivative which actually uses a slightly different way to dispatch your jobs. So basically, you don't have to know anything else about PMI. In addition to that, it is simply a protocol for correctly dispatching your jobs on the cluster through Slurm. So just a few general notes about running MPI applications. Some of the programs that you may run may be a little picky about the topology of the location of your MPI tasks. If you don't specify a specific way of ordering this, basically they will be simply assigned the way Slurm finds fit. But some codes are specifically picky about the topology, so they need contiguous distribution of the MPI tasks on the adjacent nodes. In addition to that, you may specify the number of MPI tasks per node and things like that. So the complete list of available options is available in these links, which are provided over here. So at the end, I just want to mention that there are some MPI examples which are available in this link over here. This may not be, updated, but pretty much they provide actually the basics which are required to run these examples. The only thing which you may need to change here is to, load more recent compiler and MPI libraries. So at the end, I just want to mention a few things about the hybrid parallel programming and hybrid parallel applications on the cluster. So basically, in this paradigm, you use OpenMP and MPI together, which allows you for using OpenMP, so that you do parallelization with all cores which are available on a simple compute node, but the communication between the nodes is done with using MPI. So this provides a hybrid parallel model, and it allows you for using the full power of the cluster. So there are some examples about that and some documentation which is available at this website over here. And just to conclude with the different parallel modes of, so to speak, of using different applications, parallel applications to the cluster, I'm just providing two examples of running hybrid applications. The first example is using two MPI tasks with 4 OpenMP threads per MPI task. In other words, we have 8 cores in total. So in order to execute this workflow, basically you have to specify both -n, which is the number of MPI tasks, and -c, which is the number of threads per MPI task. And also the important point is that you have to, because this is also MPI programming model, in addition to OpenMP, you have to specify the memory per MPI task here. On top of that, you have to also export the OpenMP number of threads variable, which specify the number of threads per MPI task. I know it becomes a little confusing, but this is what happens when you get to kind of heterogeneous infrastructures like the ones that we have here. And the next example shows a little kind of a larger workflow, which uses 4 nodes with 1 MPI task per node and 32 OpenMP threads per MPI task. So overall, you have 128 cores in total across 4 nodes. So in other words, you use all cores on a single node in a MPI in a OpenMP shared memory model paradigm, but the communication between the nodes is done through MPI. So pretty much that's everything that I have over here. And at the end, I just would like to give you some hints for efficient parallelization. So the first question you have to ask yourself when you get to parallelizing your code is it even worth parallelizing your code? Because sometimes, you may not have enough time to do the parallelization. But let's say if your code takes really intractable time to complete, then you may need to invest some time to do the actual parallelization. Another question that you have to ask yourself is, for example, how is compared the parallelization of established code versus, for example, starting from scratch? Let's say if your advisor gives you, established serial code and asks you to parallelize that, it may be much easier to parallelize that code because you simply can identify the hotspots in the code and try to parallelize this. But in some cases, you may not get the best performance in this way. And you may need, if you have the time, of course, and it is feasible simply to start from scratch. And this gives you also the opportunity to turn a code, which is really a black box for you, into a code that you understand, and also to get the best performance of your code. So some other general tips for parallelization: you have to increase the fraction of the code which can be parallelized. And also you have to identify the most time-consuming parts of the code and then work very hard to parallelize these parts of the code. Another important point in the realm of parallel computing is to balance the parallel workload, which means that in the case of OpenMP, to give to each thread equal amount of work, and in the context of MPI, to give to each MPI parallel task enough equal amount of work, basically, because otherwise your speed up will be really dictated from the slowest task that you have in your application. Another important point when it comes to MPI is really to minimize the time which is spent in communication, because when you add more MPI tasks, you really add to the communication overhead. And at some point, you just have to, really understand how much time goes into doing communication instead of doing only useful computational work. There are some approaches which you may use to minimize the communication, or also to hide the communication through doing just some computation. Another important thing which I figured out in my research is that using simple arrays instead of derived types, we can speed up your applications. In particular, when we're talking about MPI applications, very important is also to partition your data, because this can give you the most efficient way of using the memory. Sometimes, you may have, for instance, very large matrices or vectors, which is not possible to fit into even on a single node, so that it is important to partition the data appropriately, so that you can first fit the problem into a computer on the specific nodes, and in addition to that is to be able to use the memory efficiently. Because let's say if you have a large matrix, just going back to this example, and doing matrix vector multiplication, for instance, in MPI, you simply have to give part of the matrix and the vector to each of the MPI processes, and then at the very end, you do a reduction operation. In this way, you can save a lot of memory. Another very important topic is doing the parallel I/O. This is topic by itself, and it really, requires a presentation by itself to get into all details. But here I'm just going to mention that, for example, parallel file systems like Lustre do exist, and they allow you to do MPI parallel I/O, which means that you can use many processors doing reading and writing of data. So pretty much this is everything that I have for the time being. There are some other topics which I didn't have enough time to touch, and these are like really partitioning the data, also minimizing communication, and some others. But this should give you the basic idea what really parallel computing is, and how to use paradigms like OpenMP, MPI, and also hybrid parallel approach where you use OpenMP and MPI all together. So pretty much that's all I have, and thank you very much for your attention. So now I'm open to any questions you may have.